Alright, welcome to the Calc 1 Exam 2 review video. Let's just jump right into it. So question 1, we have a few multiple choice questions. So the first one, we know that the second derivative is greater than 0, so we know that it's going to be concave up within this interval from 1 to 9. So now we have y equals L of x represents the equation of the linear function tangent to the graph. So it's the equation of our tangent line at this point x equals 3. And so we want to know which of the following is true. Well, let's draw some pictures. So we know that it's concave up. So there's two possible orientations it could be. So for both, we're going to have from 1 to 9. But we know it could either be concave up and decreasing, it's like this, or concave up and increasing, like this. So let's say we have 3 here on both of them. And so our tangent line, if we draw that, it's going to look like this. And so what you'll notice is that the tangent line is an underestimate in both cases. So that means at L or x equals 4, say we have 4 here, right? It's going to be underneath. So for all cases, we're going to have L of 4 is less than the actual value of that function. All right, on to the next one. So here we have a graph of the first derivative of this function. And we want to determine the values of x where the local minimum occurs. So we know that when there's a local minimum, that means that around this point, so let's just call it x, we know that the local minimum, it goes from decreasing to increasing. So for f prime, it's going to be negative and then to positive. And so the only time on this graph that we're going from negative to positive around a critical point is at 3 here. Here it stays negative, and then here it's positive to negative. And notice that I'm looking at the zeros on this graph because this is the graph of f prime, and the critical points lie at the zeros, or when f prime equals 0. Sorry. F prime equals 0, f prime of x equals 0. And so that's why I was looking at those 3 points there. And I'm not looking at the top or the bottom of these humps because this is already the graph of the derivative. All right, and so that means this is x equals 3 is going to be our only answer. All right, on to the next page. We have a hot air balloon that's rising vertically. So we know that the distance of this y is changing. And so suppose x and y are the lengths of the two legs of the right triangle. So this is a right triangle. And z is the length of the hypotenuse. And theta is going to represent the viewing angle of this observer. So this observer is not moving, they're stationary. And t is the time that's elapsed. So we're relating everything in terms of time. So think related rates. All right, so which of the following expressions equations express the relationship dy dt with dz dt? Well, we know we have a right triangle, right? So we know that z squared is going to be equal to x squared plus y squared. All right, so let's go ahead and just take the derivative with respect to time for each of these and then figure out from there. So we're going to get 2z dz dt equals 2x dx dt plus 2y dy dt. And before we start comparing answers, let's see if there's anything that we can fill out, any other information we haven't used. So we don't know the rates for z and y. You know, y is changing, it's increasing, right? The air balloon's rising, which means that z is also going to be changing. But since the observer is stationary, this x, the distance, horizontal distance from the balloon isn't changing. So here we know dx dt is equal to 0. So we can kind of ignore that part there. So we're going to be left with 2z dz dt equals 2y dy dt. And so that matches this answer here. And to kind of look over the other answers why those aren't true, well, A, so you have these parts look good, except, so it looks like either they put in dy or dx dt as 1, or they just didn't pull out a dx dt, so we know that's going to be wrong. B, they took the derivatives and didn't do any implicit differentiation. C, they just plugged in the derivatives into the Pythagorean theorem, not what we want to do here. And then E, they just got rid of x, y, and z. It's similar to this one, but they don't have the x, y, and z there, so that's not going to be correct. So D is going to be your answer. All right, on to the next one. We want to suppose that f is a differentiable function, so that is good to know. And we know that f of 5 equals 4 and f of 9 equals 16, and we want to select the statement that's true. So it looks like we've got 2 that address the actual value of the function, and then 2 that address the derivative. So if you remember the intermediate value theorem, this one addresses when we have some point f of c equals some value. But notice that we have f of c equals 0 and f of c equals 3. And we're going from 4 to 16. So since 0 and 3 are not within that interval, we can already exclude these because using the intermediate value theorem, it doesn't satisfy the conditions we need. Well, what's the other theorem that we learned? The mean value theorem, right? And so this means that for a differentiable function, which we do have, and these 2 points, we're going to have f prime of c for some c is equal to this here. And so if we take our points, we're going to get 16 minus 4 over 9 minus 5. We're going to get 12 over 4, which is 3. And so this is satisfied here, which means that D is going to be our answer. All right, and for the last multiple choice question, we know that f prime of 2 equals 0, and then we're given the equation for the second derivative, and we want to know what is true. So because f prime is 0, we know that we have an extrema. So we need to decide whether it's a local min or max. Well, we know that if it's concave up, it's going to be a min. If it's concave down, it's going to be a max. So if we plug in and find f prime or f double prime of 2, we're going to get 2 times 2 minus 1 is 1 squared. It gives us 2 positive answers, mean we are concave up. So because we're concave up, it is going to be a local minimum. On to question 2, we're just going to compute the following derivatives, and we don't want to simplify. All right, so for this first one, let's go ahead. I'm going to rewrite the function. We have f of x equals 4 to the x minus 4x to the 4th minus, and then we have x over 4, but I'm going to write that as 1/4 x just so we can see that a little more clearly. All right, taking it term by term, let's take those derivatives. So first we have 4 to the x. So even though we have this exponent here, notice that x is the exponent, it's not the base. So we are going to use this rule that d dx of a to the x is equal to a to the x natural log of a here. So we're going to get, our a is 4, so we're going to get 4 to the x times natural log of 4. All right, on to the next one. This one here, this is just a simple power rule. Bring down the 4, so 4 times 4 is 16, and decrease that exponent by 1, we're going to get cubed there. And then finally, another power rule, we just have this coefficient that comes down, and that's our derivative. All right, this next one here is going to be using chain rule. So we have y equals the natural log of x raised to the 5th power. And so we need to take the derivative of the outside and multiply it by the derivative of the inside. So dy dx, well, first we're going to bring the 5 down, right? Keep the inside, decrease that power by 1, and then we're going to multiply by the derivative of the inside. Remember, the derivative of the inside is going to be 1 over x. So we're going to get that 1 over x there. And we can write that as all of this over x as well. Either of those will work. And there we go. All right, so question 3 goes over L'Hopital's rule, and this is not on this exam. So I'll be skipping that question and only focusing on 4. So we want to find the slope of the tangent line at this point. And so remember, the slope of the tangent line is going to be that dy dx. And so what we can do is we take this function and take the derivative implicitly. So I'm going to start by doing y sine of x equals 4x cosine of y. All right, starting on the left side, we have product rules on both sides. So we're going to start by taking the derivative of y is just going to be 1, and because we're doing implicit differentiation, we're going to get a dy dx here. Keep the sine x, right, because we're doing product rule. So we did derivative of the first times the second, plus keep the first, take the derivative of the second. Derivative of sine is just cosine. All right, on to the right side. Take the derivative of 4x. We're going to get 4, keep the cosine of y, and then add, keep the 4x. And what's the derivative of cosine of y? Well, cosine is going to give us negative sine of y. And because we're doing implicit differentiation, we're going to get that dy dx there. So we're taking the derivative with respect to x. So when we're taking derivative of anything with x, we can treat it normally, but if it's a y, we bring out that dy dx. And we're trying to solve for dy dx. So I'm going to move some things around to try and get that dy dx, all of those on the same side. So I'll keep the sine of x here, bring this term over. So there's a negative here, so we'll be adding it. And then I'll bring that term over. And then I'm going to pull out a dy dx from both of these terms. All right. So from this point, you could divide both sides by this here, but I'm just going to go ahead and plug our point in and then divide later since this is a little ugly. So we're going to get dy dx sine of x, so remember x is pi over 2, so that's going to actually be 1. Then we're going to get 4 times our x, which is pi over 2, and then sine of y. Well, sine of y, so that's going to be sine of 2 pi, that's going to be 0. All right, on to the next side, we'll have 4 times cosine of y, so cosine of 2 pi is going to be 1, and then subtract 2 pi is our y times cosine of x. Cosine of pi over 2 is 0. And so this term's going to 0 out, that one will 0 out, so we're left with just dy dx on this side and 4 on that side. So that is going to be our slope of the tangent line. On to the last question of the review. So we've got this track here. We've got a television, a camera at this point here, and it's positioned 340 meters from the closest portion of this backstretch. So theta is going to be that angle of the cameraman's sight with that lead car. It looks like that green car there. And then we want x to represent that, basically that hypotenuse length when we form that right triangle. And we want to find the rate of change of the rotating the camera. So we want to find d theta dt. And it gives us, at the moment, the car is exactly 486 meters from the TV. So they give us x at some point 486 meters. All right. And then another piece of information they give us up at the top is that the cars travel at a constant speed of 94 meters per second. And so that's going this direction. So if we label this y, let me rewrite that. That means our dy dt is equal to 94 meters per second. All right, now let's start setting up an equation to see if we can find what d theta dt is. So we have x and y here, and we also have this 340 meters. So we could try and set something up with this hypotenuse, but we don't know anything about the rate of change of x. But we do know that because this 340 meters is constant, we do know its rate of change. Its rate of change is 0. So let's try and use that side because that'll simplify our equation a little bit more. And remember, we want to use theta. So if we have both side lengths, we're going to have tangent of theta is equal to opposite y over 340. So that'll give us y is equal to 340 tangent of theta. And then from here, take the derivative with respect to time. So we're going to get dy dt is equal to 340, and the derivative of tangent is secant squared theta. And then we get that d theta dt. Remember those related rates. And so here, we're trying to solve for d theta dt, and we do know that dy dt is 94. So we're going to get 94 is equal to 340 secant squared d theta dt. And so generally, we know that d theta dt is going to be equal to 94 over 340 secant squared theta for any value of theta. But they want us to find that rate at this exact moment when x is equal to 486 meters. But to solve for it, we only need theta, right? So let's go back to our triangle. Well, we want this theta whenever we know this is 340, and we want to know when that hypotenuse is 486. And so we can solve for theta using these two side lengths, using cosine. It's going to be 340 over 486. So theta is going to be arc cosine of 340 over 486. And so d theta dt is equal to 94 over 340. And just to simplify this a little bit, since we do have this cosine here, you can just plug that into your calculator. That's totally acceptable. But a cool thing we can notice here is secant squared is the same as 1 over cosine squared. And so since it's already in the denominator, we actually are going to get this cosine squared of theta here. And so what we'll end up getting is, well, we have cosine of theta, which is arc cosine of this. So those are going to cancel out. It's that squared. So you'll get 94 over 340 times 340 over 486 squared. And then from here, you can plug it into your calculator, and we're going to get 0.135, and then it's going to be radians per second, since our theta is in radians and our t is in seconds. So that's going to be our final answer.